Okay, so I hope people will be taking their seats, and it's a pleasure to welcome you all to our second day of Stringed Math. Especially congratulations to all participants from Italy and Iceland. Great job. I feel kind of sorry for England. In the past few days, lots of bad things are happening, and I can't only imagine what's going to be next. Well, anyway, so back to business. It's my great pleasure to introduce Hiraku Nakajima, and he'll tell us about quantized Coulomb branches of 3D n equals 4 gauge theories and difference operators.
Thank you very much. So I'd like to thank organizers for the invitation. It's a great pleasure to give a talk here. So I will talk about quantized Coulomb branch of 3-dimensional n equal 4 supersymmetric gauge theory. So this is based on my work and my joint work. In fact, there's a typo here, and the third paper, the number for the third paper is wrong. But anyway, the first half of my talk is a review of general definition of a Coulomb branch, not quantized one. So I already gave a talk on the ordinary Coulomb branch several times. So I apologize that if you already heard many times, then I just need to repeat. So I first reviewed the Coulomb branch of 3-dimensional n equal 4 supersymmetric gauge theories. So this is for mathematicians, and I explain how I didn't understand physicists' definition of Coulomb branch. Okay, anyway, let GC to be a compact Lie group, and I take its complexification, G. So I will mainly use this reductive group G. But I start, for this part, I just consider also a compact Lie group. So let M be a quaternion representation, GC. So this is a finite dimensional representation. It's defined over quaternion vector space. And if I use this reductive group, then it is regarded as a symplectic representation of G. Then physicists consider 3-dimensional n equal 4 supersymmetric gauge theory, and also, in fact, they also consider the 4-dimensional n equal 2 supersymmetric gauge theory, and this 3-dimensional gauge theory is given by dimensional reduction. So it means, so physicists wrote down some particular Lagrangian, and they consider partition function, correlation function, and so on. This part, I don't understand completely, but somehow it is still half understandable. But then this is some big step. So physicists also consider associate a Coulomb branch to the gauge theory. So this is a non-compact hyperkähler manifold, possibly with singularities, and SU2 action, rotating complex structure. So hyperkähler manifold has a complex structure IJK forming two sphere, and SU2 acting on this two sphere. Then, as far as I understand, this Coulomb branch arises in this way. So you consider the gauge theory, and physicists consider the so-called effective theory. And under some assumption, so this gauge theory is equivalent to the sigma model which target this Coulomb branch. And this is true when the so-called Higgs branch of the gauge theory is just consistent of 0, and MC is smooth. So this Higgs branch is defined as the hyperkähler quotient of the vector space M by this compact Lie group GC. So today I will not consider the Higgs branch, but it occasionally appears in my talk. Then 1996, Seiberg and Witten computed the Coulomb branch for the case when GC is SU2 and M is equal to 0. So this is, they originally computed the Coulomb branch for 4-dimensional theory, and 3-dimensional theory is somehow can be obtained by a kind of reduction from the 4-dimensional answer. So anyway, they obtain the Coulomb branch, they identify the Coulomb branch with the so-called Atiyah-Hitchin manifold, so which is a modularized space of centered SU2 charge to magnetic monopole on R3. So anyway, so this is a nice hyperkähler manifold and have various nice properties. Then after Seiberg-Witten's paper, there are lots of subsequent works computing this Coulomb branch in various examples. So people take various GC and various M's and they compute. And sometimes the Higgs branch is not, Higgs branch is non-trivial, and in that case, the Coulomb branch is singular, often singular. But the definition of the Coulomb branch, which I just briefly explained. So this gauge theory, I mean, this is the equivalence of the quantum field theory, and for mathematicians, there's no rigorous definition of the quantum field theory, in particular for this kind of supersymmetric gauge theory. So this definition is naively fine, but I don't quite understand as a mathematician. So at that point, I think I heard this that talk by Witten in Newton Institute in 1996. He explained this work of Seiberg-Witten, and it was very interesting. But somehow I couldn't really understand because the definition of the Coulomb branch is not clear. Then 70 years later, 2013. Clemmency, Hanani, and the following give a combinatorial expression of this character of the coordinate ring of the Coulomb branch. So this is the so-called monopole formula. So I will not go into the detail of this monopole formula, but this formula is mathematically meaningful. So it is some expression and the sum over the co-weight lattice. So this expression perfectly makes sense mathematically. So this is a big hint to understand the Coulomb branch. So maybe I should explain. So this MC is, as I said, the hyperkähler manifold, but it has a natural algebraic structure. So I consider the ring of algebraic functions on this Coulomb branch. So this is called Kähler ring in physics literature. Then, as I said, on MC, you have an SA2 action, rotating hyperkähler structure. And if I pick up a particular complex structure, then U1 among SU2 preserving this complex structure. So the ring of algebraic function on this Coulomb branch is a representation of U1, or it extends to the C star. So then, in some cases, this weight space with this C star action is finite dimensional. So of course, I mean, MC is non-trivial variety. So the coordinate ring is infinite dimensional vector space, but its character is a formal sum is meaningful. So anyway, so this monopole formula is a mathematically meaningful expression. So I try to look for a mathematical definition. So now I explain my proposal of a mathematical definition of the Coulomb branch. So idea is simple, I think. So suppose we have a topological quantum field theory given by a twisting of a supersymmetric gauge theory. In fact, in some example, there are several attempts to realize this topological quantum field theory. So this is not so big assumption, I think. So anyway, then because TQFT assign invariant to 3 manifold and vector space to 2 manifold. So I consider the Hilbert space for the particular 2 manifold S2. Then this Hilbert space for S2 is a commutative ring acting on the Hilbert space associated with the Riemann surface of genus G. So this is a picture. So I have sigma G, and this is a 3 manifold with 3 boundaries. So I have sigma G for the bottom and the sigma z on the top and S2 in the middle. Then this 3 manifold gives a vector in the Hilbert space for the boundary. And in this case, we have three boundaries. So this is a tensor. So one is the opposite orientation. So maybe S3 is also opposite direction. So anyway, so this is a tensor product of Hilbert space for S2 and the sigma z to Hilbert space for sigma z. So if you know that the two-dimensional topological quantum field theory is corresponding to Frobenius algebra, then this is just the same construction, just one-dimensional up. And because S2 can be moved in 3 space, this is a commutative algebra. First of all, multiplication is just you just take one more copy of this picture and just connect it over this picture. Then, because S2, you can move S2, this is commutative. And so this doesn't make sense if we don't know this quantum, the Hilbert space. But as I said, there are many attempts to realize topological quantum field theory. And in mathematical works, for example, Donaldson and Flares and Klonheim and Morfkers, they define the quantum Hilbert space associated with sigma z as a cohomology group of the moduli space of nonlinear partial differential equation, such as, so for the case GC is SU2 and M equal in 4 dimension, if you consider in 4 dimension, this is the instanton equation, and its dimension reduction to 3 dimension is just flat connection equation. And for GC is U1, the M is just one-dimensional quaternion. Then this is the so-called, in mathematical literature, this is called the Seiberg-Witten equation. So it's a certain nonlinear partial differential equation, and you consider the modular space of nonlinear partial differential equation and take just its cohomology group. This is a conventional approach to defining TQFT associated with this gauge theory. So there's one point which you must be careful a little bit, because if I formally consider the modular space on 2 sphere instead of genus G Riemann surface, then for example, if for flat connection, there's no flat connection on a sphere, because S3 is a fundamental group of S3 trivial. So there's only trivial connection. So its cohomology is trivial. But as I said, this for SU2 and M equals 0, the Coulomb branch should be at the Hitchin manifold. So this answer is certainly not correct. So I slightly modified it. But so far, I cannot really explain in full detail of this step. But anyway, so to get the correct answer, it is the monopole formula, as I said, is mathematically rigorous. So I try to reproduce monopole formula. So this is quite monopole formula helps to consider help me to consider this answer. So anyway, so far this answer makes sense only when M is of this form. M is n plus n star. But this is a rather mild assumption, and in many, even under this assumption, there are lots of many interesting examples. So anyway, instead of there's another typo here. So instead of just considering the modular space of solution, I consider the correspondence. So this is roughly the pairs of the, it's a subvariety in the product of the modular space. So this is called Hecke correspondence. So sorry about this typo. And so if you only consider the bundle, then this Hecke correspondence is basically the usual Hecke correspondence. But I also assign, because you have this vector space representation of the group, I also assign at the sections to the Hecke correspondence. So this is a modular stack of quadruple, so P1 and P2 and phi and S. So P1 and P2 are holomorphic G bundles on the formal disk. And phi is isomorphism between P1 and P2 over the formal disk minus the origin. So P1 and P2 are almost isomorphic, but they differ at this origin. So it's P1 is obtained, P2 is obtained from P1 by some kind of slightly changing the transition function at 0. And S is a holomorphic section of the associated bundle, or maybe again and the type. So this is G. So P1 associated bundle to P1 to the representation N. And if I send this S by phi, because this phi has a pole at the origin, phi of S is in general not holomorphic. So this is a rational section of the associated bundle. So I assume that phi S has no pole at 0. So basically, Hecke correspondence is just the pairs of bundles which are isomorphic outside the origin. And there's also one section S, which, because of this reason, you can regard S as a section of both P1 and P2 simultaneously. And this is an intuitive picture of this correspondence. So I consider this S sphere is very small. Then, so I consider that this time direction, I consider the effect of this two sphere on the top Riemann sphere and Riemann surface and the bottom Riemann surface. So because S2 is very small, these bundles are different only outside you can forget the outside of this formal neighborhood of D. And because this S2 is very small, in fact, not only D, so it differs only just this point. So P1 and P2 are isomorphic. And the section lives on the whole space, so it must be in the section of both P1 and P2. So I hope this naive explanation is natural, so you accept this definition to be natural. But anyway, so this definition works, so I'm very sure that this definition is correct, at least under this assumption. So this is a modular stack. Because of the automorphism, this is of infinite type, but you can work on its cohomology. More precisely, it's Borel-Moore homology group. Then there's a natural convolution product on this Borel-Moore homology group. So this is the usual definition. So you consider P1 and P2 and also another bundle, P3, and the section is a common P1, sections of P1 and P2 and P3. Then you have a map into P1 and P2 and P2 and P3 and P1 and P3. So by using this diagram, you can define the convolution product. So this is the usual definition. Then lemma is this is commutative. Then I just define COMC as this cohomology group, a homology group with this convolution product. So this is a commutative algebra. And this has nice properties such as finitely generated and so on. And so because MC Coulomb branch can be recovered from this ring as a affine algebra. This MC is a spectrum of this commutative ring. So this recovers Coulomb branch as an affine algebraic variety. And there's a C-star action because this C-star action on the space is corresponding to weight space decomposition on the coordinate ring. And here you have natural grading given by homological degree. So there's some technical collection term, which is basically harmless. So you can just consider this to be is given by homological degree. And then you compute the character of the coordinate ring, which is basically just a computation of the Poincare polynomial of the space R. And R has a nice decomposition into stratums, and each stratums are vector bundle on some homogeneous space, which has no odd cohomology. So by this stratification, you can compute Mayer-Beatle sequence, but because there's no odd homology group, this Mayer-Beatle sequence just split. So you can just compute the Poincare polynomial. And in some cases, this Poincare polynomial just diverges because the weight space of the sister action may not be finite dimensional in general. But when the degree, under some assumption, the degree is always non-negative, under this condition, the weight space is finite dimensional. And this character is just equal to monopole formula. So this seems to be right answer. So I give you a trivial example, too much trivial, sorry about it. So I take G to be C star and N to be just 0. So this is the simplest example. Then this P1 and P2 are just trivial line bundle over the formal disk. And the isomorphism phi is given by this, Z to the power K. So K is just integer. So this is non-zero outside 0. So yeah. So phi is the isomorphism outside the origin. So for each integer k, I have this isomorphism. So the space R is just a collection of points parametered by integers. And one thing you must be careful is that there's automorphism. So I consider moduli stack. So I don't forget the automorphism. So this cross is not a single point. You have automorphism of C star. So each point is a classifying space of the C star. And the multiplication of ith point and the jth point is just given by I plus jth point. So this is, I don't give the definition of convolution product, but I hope you can imagine that should be the most natural product in this picture. Then this Borel-Lemoine homology of the space R is a direct sum of copies of the classifying space, and this homology of the classifying space is just a polynomial in one variable, which I denote by W. And I take a copy of a K and Z. So I also have another variable X, and also I need to allow the negative pairs, X and X. Then this is a some ring, and I just compute its spectrum. It's just the C cross C star, or T cotangent amount of C star. So this Coulomb branch is something close to this example, but in general, you must be, somehow it is modified from this. So I have two remarks. So when G is torus, then the space is always like this. So you have a bunch of points, or a vector bundle, or a vector space, infinite dimensional vector space over each point, and it's homology. For each component has trivial homology group, and the multiplication is not so difficult to compute. So at the end, we get explicit presentation of this coordinate ring when G is torus. And also, so there are, in this, as I illustrated in this example, there are many connected components. And in general, connected component of the space R is bijective to fundamental group of G. So you have additional grading on this, because this decomposes into connected components. So you have additional grading. So on the Coulomb branch, spectrum of the coordinating, it means that there's action of the Pontryagin dual of the fundamental group. So if G is semi-simple, then phi 1G is a finite group. So this is not, Pontryagin dual is a finite group also. This is not so interesting. But if G is, for example, a general linear group, then phi 1G is G. So its Pontryagin dual is C star. So if G is general linear group, it means we have C star action on the Coulomb branch. So this is an example. So C star action, in this example, is just rotating this C star action. Okay, now I will talk about quantization. So because of this definition, so there is one natural deformation of the construction. So I consider the modularized stack of triples, and so this is defined over the formal disk. And over the formal disk, you have the rotation action of C star. So I also put this. I mean, in physics literature, this is called omega deformation. So I consider equivalent C star equivalent cohomology of this infinite dimensional space. And then this is a deformation. More precisely, this is the free module over the equivalent cohomology of a point, and whose spectrum is just C. So this is the deformation of A star R, a commutative coordinate ring of the Coulomb branch, parameterized by C. So I usually denote the point in C by H bar, so Planck constant. And by the same reason, it has a convolution product. You could just consider three projection considering triple product. And this projection is C star equivalent, so this convolution product is still defined. Well, I didn't explain the proof of the commutativity, but anyway, so this proof for the commutativity fails if I consider this C star action. And if you remember my naive explanation, so I put also another S2 to consider the multiplication, and the commutativity is just follows because I can swap this S1 and this S1 in three-dimensional type. But you cannot swap it under S1 equivalence. So in this sense, you cannot expect the commutativity if I consider C star equivalence. And in fact, it's not true. And I mentioned that this Coulomb branch is a hyperkähler manifold. And in particular, if I pick up a complex structure, this has a complex symplectic form. And this is non-commutative. And if I take the first leading part of the commutator, this is a Poisson bracket on this, this symplectic, complex symplectic variety MC. Yes. Yeah.
Which part of the data of the data of the sphere inside?
Well, I mean, S2 is. So he asked the difference between the disk and S2, right? That is basic. This is the basic request. Yeah. So that part I don't quite understand well, but as I mentioned, that if I just stick to the moduli space on two sphere, I cannot get the correct answer. And if I don't put the stability condition, then the space is very close to this space. And in fact, in my first paper, I used this S2, and I computed it, computed the Poincare polynomial, and it gives me the correct answer. So at this moment, I believe this definition is natural, but I'm not also surprised if someone can use this modular space on the two sphere without stability condition to produce similar kind of construction. So in that sense, I cannot answer your question. Then, so this is the definition of the quantized Coulomb branch. So this is a non-commutative algebra which deform this commutative algebra. And I go back to this example, G equals C star and N equals 0. In that case, I have C cross C star. And there is a two way to consider the same. So the algebra is W and X inverse. The commutator relation is modified to this relation. X plus minus and W. Commutator of X plus minus and W is H bar times X plus minus. There are two ways to understand this ring. One is you consider X to be the coordinate on the torus, C star, and the W to be differential operator. Another is considering W is a function on the Lie algebra, and X as a difference operator. So today, I will explain the reason soon. I consider W to be a function on the Lie algebra, and X to be a difference operators acting on the W. So this is the first example of quantized Coulomb branch. And in general, for arbitrary G and N, because I defined the quantized Coulomb branch by using the equivalent cohomology, there's lots of tools to analyze this equivalent cohomology, namely the localization theorem in equivalent cohomology. So if I consider the fixed point, and fixed point have the similar description, and from this consideration, you can obtain the embedding of this Coulomb branch for general G and N into the Coulomb branch for the maximal torus and with representation 0. But you invert all roots. And the roots are functions on W. So by this reason, I consider instead of differential operator on the torus, I consider difference operators on the Lie algebra. And I consider this larger ring as a ring of difference operator with poles along root hyperplanes. So this is a general result. And moreover, when G equals general linear group, or more generally, if G is a product of general linear group, I can do a little bit more. So in this Hecke correspondence, there's some nice smooth closed subvariety. This is well known in the context of the geometric Lagrange. So I consider pair. So for GLK, it means I consider the rank K vector bundles on formal disk. So I consider pairs of vector bundles E1, E2, and phi, and S. And phi is given by the following correspondence. So I consider E1 as a space of sections, holomorphic sections, sheaf of holomorphic sections, and E1 is a subsheaf of E2, and it is subsheaf of E1 with poles at 0. So this correspondence often appears in, this is the original definition of the Hecke correspondence for general linear groups. Or I can switch the role of E1, E2, and I can consider this. Then miracle is that R is generally very singular variety. For this general linear group, this is a smooth closed subvariety. Then I can consider its fundamental class. So this is a perfectly well-defined homology class of R. So this can be considered as an element of the Coulomb branch or its quantization. And this, because this is given by the fixed point formula, and once you have the homology class represented by a smooth cross-subvariety, you can just compute the image, its image, by using localization formula, usual localization formula. So you just compute the normal bundle, Euler class of normal bundle. So this kind of consideration, realization of this quantized Coulomb branch to the Coulomb branch for the abelian gauge theory was appeared in the paper, physics paper, Limov and Garrod. So this is very useful for if G is general linear group or its product. We obtain explicit difference operators in this with poles along hyperplanes, and you just compute what they are. So this is an example. So I take the simplest case. So G is general linear group, and N is a adjoint representation plus L copies of vector representation. And this is the so-called quiver gauge theory associated with this Jordan quiver. So I have this vertex, and this is a framed vertex, and I consider this is Jordan quiver. The upper part is Jordan quiver. This is a framed vertex. So anyway, this is a representation. Then, by the way, I should say, so this has, so E1 has degree something, and this has degree something plus k, and E2, you can consider the degree of E2 as integer between 1 and k minus 1. So there are k minus 1 components. Let me see. Maybe I should exclude k. Yeah, n should be 1 from 1 to k minus 1. So anyway, according to this homology group, I can write down the corresponding homology class, fundamental class, as an explicit difference operator, as I said. So this is the answer. So it's a sum over the all subset in 1 to k, whose cardinality is equal to n, and description. And this operator, if there is no this part from A equal 1 to L, so it means if I consider L equal 0 case, then this difference operator is McDonald operator appearing in this. I mean, this is not precisely mean. So this is a more precisely rational degeneration of McDonald operator appearing. So the simultaneous eigen function of this McDonald operator is famous McDonald function. And this is a rational degeneration. So in this case, in this particular case, this is simultaneous eigen function in Jack polynomial. And if there's this term, so in that sense, this is generalized McDonald operator. But this additional factor is also natural, and by using description, we prove that this quantized Coulomb branch for this example is the spherical part of the so-called cyclotomic rational Cherednik algebra. So associated with the least product of symmetric group and cyclic group. And the answer for the Coulomb branch has been known before, and it's go back to 1997, work of Borg and Oglio notes. So this is symmetric case symmetric powers of the quotient, type A quotient singularity. And this cyclotomic rational Cherednik algebra is spherical part of the cyclotomic rational Cherednik algebra is natural quantization of this space, which has been studied by various people. So this is the first remark, and the second remark. So we have the similar kind of similar operators for finite AD quiver, and in this case we prove that the quantized Coulomb branch is so-called shifted Yangian. So I conclude problems with problems. So this construction just gives us the coordinate ring of the Coulomb branch. So it's natural to ask what is the hyperkähler matrix in this definition. So because this is basically algebraic construction, I don't think we can give a hyperkähler metric explicitly. So, but still, twistor space is basically some algebraic variety. So you can hope to give a definition of twistor space. I hope this is not so. In four-dimensional description of the hyperkähler metric is, as we all know, that this is very difficult problem. But in three-dimensional case, hyperkähler metric has SU2 symmetry, so it's much simpler. So this is not hopeless. This is not so difficult question problem, I hope. And the second is determine the quantized Coulomb branch of quiver gauge theory of affine eddy type. So my previous example is considered as Coulomb branch of quiver gauge theory of Jordan type. So Jordan type is the very first affine eddy quiver. So it's natural to consider the more general affine case. I mean, of course, you can consider arbitrary quiver, but somehow I think that we don't know what is the Coulomb branch for the quiver gauge theory of arbitrary quiver. For example, you can consider the star-shaped quiver, and this Coulomb branch is Higgs branch of the Higgs branch of class S theories, of whose description was asked by Moore and Tachikawa in this string mass conference in some years ago. So this symplectic variety is something which we didn't know. So in general, I don't know what is Coulomb branch for arbitrary quiver, but for affine eddy types, the conjecture is that this Coulomb branch, at least for the ordinary commutative Coulomb branch, is a moduli space of instanton of multi-turbinate space. And this conjecture was proved for affine type A in my work with Takayama. So this seems to be a reasonable conjecture. And other is a little bit more ambitious problem. So I consider only basically Hilbert space for S2. But it seems, I mean, also there are many attempts to construct Coulomb TQFT associated gauge theory. So it's natural to ask more general to ask to construct TQFT. More general TQFT for what is the Hilbert space associated with higher genus Riemann surface, and what are the examples of invariants arising in this way. Invariant of three manifold or three manifold with nodes or rings. And for quantization, I used the S1 action, so I cannot expect a full TQFT. So this TQFT, I need to assume that the three manifold has S1 action. And another interesting problem is, so this quantized Coulomb branch is Coulomb branches are some interesting non-commutative algebra. So the spherical part of the Cherednik algebra has been studied by many people. And one interesting aspect, point in this study of representation theory is the so-called symplectic duality proposed by Braden, Rickert, and Wood, Webster. That is a relation between the quantized Coulomb branch and the quantized Higgs branch. So Higgs branch is a Hamiltonian reduction of vector space by group. So you can consider, instead of hyperkähler reduction, you can consider it a symplectic reduction by a reductive group. And then because this symplectic vector space has a quantization by difference operator. So if I decompose M into n plus n star, then the M can be quantized by differential operators on n. Then you can consider quantum Hamiltonian reduction, which is a definition of quantized Higgs branch. Then this symplectic duality expect there's some relation between the quantized Coulomb branch and the quantized Higgs branch. So this is many people are working on, and that is an interesting topic. And also another is, so as I said, 4-dimensional Coulomb branch associated with R3 cross S1 is much more difficult, and it is a hyperkähler manifold, and in many cases it's Hitchin space. And so with this, I understand from Gaiotto that if I consider the K-theory instead of homology group, then the definition perfectly makes sense. So instead of equivalent homology group of space R, I just replace equivalent homology by equivalent K-theory. So then, because the convolution product is just you need pull back and push forward, so this makes sense for equivalent homology. So this perfectly makes sense, and the expectation is that the corresponding variety is the Coulomb branch for 4-dimensional gauge theory, but it's another complex structure which is different from this as a modular space of Higgs bundle. So it's a complex manifold. It is expected to be isomorphic to this character variety. Okay, I stop now. Thank you for attention.
Well, this is rare occasion where a speaker finishes before time limit, so I encourage everyone to follow this lead, so we have quite a few time for questions.
Is it possible to describe what happens to the equivariant cohomology if you go to the singular Coulomb branch? So if I understand right, your computations of equivariant cohomology were in the case where the Coulomb branch is smooth.
No. The Coulomb branch is singular in general, but okay. I describe some smooth subvariety in a singular space.
Okay, so then I guess I can ask the question in the other direction. What happens to the equivariant cohomology if you make the Coulomb branch smooth?
Coulomb branch cannot make smooth. I mean, it's somehow Coulomb. I cannot change the definition of the Coulomb. How to say? What do you mean by? Maybe I still don't quite understand. Coulomb branch is in general singular because I just defined as spectrum of the commutative ring. So this is affine algebraic variety. So I cannot distinguish. In fact, it's very difficult to determine the smoothness of the Coulomb branch. So for example, I don't know some description of the smooth locus of the Coulomb branch. So this is some abstract definition. I just define the Coulomb branch as a spectrum of some commutative ring. So this is I only consider the global function. And to study the local structure of the Coulomb branch is a difficult question.
Other questions?
Yeah.
Okay. Now, just a question to your last phrase you want to say about K-theory, because as I understand, your varieties are still kind of symplectic varieties. Classical varieties have 0 periods. Yeah, symplectic form is exactly.
R is not symplectic variety.
Sorry?
R is not symplectic. R is an infinite dimensional variety.
No. But
MC, the Coulomb branch.
Yeah,
Coulomb branch is
symplectic. Yes. And if you if even quantize, you still get something like differential or difference operators. But in K-theory, would you get quantization of something of trigonometric type?
Trigonometric.
So to be close to some character, maybe wild character varieties. I see.
Yeah, in this example, so this cyclotomic rational Cherednik algebra is is rational version. And in fact, if I consider the case area on this corresponding to this example, this is the cyclotomic trigonometric Cherenkov algebra. But in fact, that was not known, and this is a new algebra. And if the L equals 0 case, then rational Cherenkov algebra. Maybe yeah, this is not quite good. So if K, this L is equal to 0, then this is so-called trigonometric Cherenkov algebra instead of cyclotomic rational Cherenkov algebra. And if I consider the K theory, then I get ordinary Cherenkov algebra. So this is trigonometric.
And could it be some kind of cluster variety again? Or?
Yeah, that is a nice. I mean, in some example, people expect this to be cluster variety, but we don't know in general.
Yeah, just a naive question. So in your construction, you had to pick a Riemann surface of genus G. Can you comment on the dependence on the construction on the genus?
I hope this is TQFT. So this is this vector space forms a vector bundle on the modular space of Riemann surface.
But the algebraic variety MC does not depend on G, right?
So this, so as I said, the vector space is a representation of the S2. Z of S2 is gives me a variety, and the Z of sigma G is expected to give a vector bundle or sheaves on this Coulomb branch, and which I hope which is independent of the choice of complex structure. So in this definition, I consider the holomorphic vector bundle. I mean, I only used the formal disk, so it doesn't make much sense. But if I just naively generalize this definition to the case of Riemann surface, then it a priori depends on the complex structure. But at the end, the answer should be independent. That is my hope.
How high do you think you can go in dimension? Meaning you can probably do 5-dimensional gauge theories by some sort of elliptic.
Yeah, so I'm just scared about this elliptic cohomology. And first, I must learn what it is. But yeah, so people say that this you can just go to higher and higher and 6 dimensions. So that might be possible to consider.
Any other questions? Well, if not, let's thank Hiraku for a wonderful talk.